All right, welcome back, everyone. It's my great pleasure to introduce today's speaker, Fang Yan Chen from Chongqing Normal University, who will speak to us today on a special class of Hermitian threefolds. So thank you.
Yeah, thanks, Jeff. Thank you very much for the invitation, and thank you all for coming to spend your precious time. I'll try to be brief. I think it will take me maybe 15 minutes or so. So the topic I like to talk about today is a special kind of Hermitian manifold, compact Hermitian manifolds. With a high restriction on its differential geometry. So I'll divide the talk roughly into 4 parts. So in the first part, I'll give some background, which I'll be brief because I noticed the audience here are pretty much experts. So I'll try to be brief here, but that's prepared for a general audience, that part. So the second part is the technical terms on the 2 special types of Hermitian manifolds that we're interested in, which we call BKL and the BTP. I'll explain what they are. So the third part will basically be our first result in this report, which is a characterization theorem for BTP manifolds. And the fourth part is our second result, which gives a classification of in the complex three-dimensional case. Okay, so so this talk is based on joint work with Chuanting Zhao from Central China Normal University, another normal university, but in the neighboring province. So we're basically interested in understanding a special type of threefolds. So basically involving the so-called Bismuth connection, aka Strömger connection. So first of all, let's recall that Hermitian manifold is just a complex manifold equipped with a Riemannian matrix that is compatible with almost complex structure. Giving any complex manifold, you always have this kind of metric. So once you equip the complex manifold with a Hermitian metric, then there are several canonical metric connections on M. So the first one, of course, is the Levi-Civita connection, which is available, uniquely exists on any Riemannian manifold. That's the unique metric connection that is torsion-free. So torsion is this symmetry terms measured against the Lie bracket. So, but this connection, this Levi-Civita connection, which we denote as D, may or may not be compatible with the almost complex structure J, right? If it does, then the metric is called a Kähler metric. So in this case, the Riemannian world fits perfectly with the complex world, right? So that's Kähler geometry, which is well known and well studied. But when this manifold doesn't sometimes it doesn't admit a Kähler metric. For instance, in the compact three-dimensional complex manifold case, one could say that the majority of them are non-Kähler. For example, all these twistor space, right? Their fundamental group can be any finite present group by Topp's famous gluing theorem. So there is, one could argue that there is the need, just from the pure differential geometric point of view, there is the need to study Hermitian geometry when the matrix is non-Kähler, right? So-called non-Kähler geometry. So in this case, the Levi-Civita connection is not the most suitable tool to use. The reason is that you could study its differential geometry, namely the Riemannian geometry, but it's unclear how the result is related to the complex analytic property of the manifold, which is something you like to study to begin with, right? It's a complex manifold. So people often, I mean, it's related, but this relationship is kind of implicit. It's not very easy to use. So in practice, people use another connection, namely the Chern connection, which we denote as nabla C. So this is a connection compatible with the metric and almost complex structure. And also the torsion has only 2-0 part. So there's no 1-1 part. So which can be described by this equality. So such a connection exists, uniquely exists on not just the tangent bundle, but any holomorphic vector bundle. So basically, it just requires the connection to be compatible with the metric and also compatible with a full complex structure. So, so that's where complex geometers use the most, right? In algebraic geometry, people use this connection. So besides Levitivita and Chern, there's another canonical metric connection that is called Bismuth connection. This is kind of a, so the definition is that it's the unique metric connection that is compatible with J, and also the torsion is totally skew symmetric. Namely, torsion is a 2-1-2 tensor, right? So for the XY part, it's certainly skew symmetric by definition. But if you use the metric to pour back the Z part, then it becomes a 3-0 tensor, right? So you wanted the 3-0 tensor to be also skew symmetric with the last two position. So it becomes a 3-form, right? So when you impose this restriction, then the Hermitian connection becomes unique. So that's called Bismuth connection. And the Bismuth connection serves as a bridge between Levitivita and the Chern. In a way, here I'm trying to understand it from the mathematical point of view. I don't know much physics, so so in a way, it's Riemannian geometry is not as good as Levitivita, but better than Chern. In a sense, my understanding is that its torsion is somehow smaller than the torsion of the Chern, in the sense that it doesn't have a symmetric part. For example, the geodesics are described by the geodesic equation, which only use the symmetric part of the connection, right? So therefore, Bismuth connection and the Riemannian and Levitivita connection share the same set of geodesics. So if you do this comparison geometry stuff, then you know, in a way, it's certainly better than Chern. But on the other hand, from the complex structure point of view, Bismuth connection is certainly not as good as Chern, because it's compatible with J, but not compatible with D bar, right? But on the other hand, it's way better than Riemannian connection, than Levitivita connection, because D in a non-killer case is not even compatible with J, right? So, so in a way, it's a compromise. But somehow the physicists, they must have their intuition and reason. They just use this Bismuth connection a lot. So only in recent years, when we were interested in this Bismuth connection, we found that it actually has, in a way, more rigid than other Hermitian connection, including Chern or Levitivita. So this connection somehow is very, very unique in a way. So to summarize, so when the Hermitian metric is scalar, then all these three metric connections are the same, right? So we have just one kind of geometry. But when the metric is non-scalar, then they're mutually distinct. So we have at least three different kinds of geometry. So now I'm a differential geometer, so we study things in purely differential geometric perspective. So when you have a connection which just gives you a way to do calculus on a manifold, right? So so you ask some simple-minded questions. For example, what kind of, so for this connection, what kind of manifold, what kind of space are space forms, meaning that they have constant curvature in some sense, right? for example, for bismuth connection, you could ask, what are the bismuth space forms, right? So, and then because this connection is also with torsion, so you could also ask issues about torsion. When would the torsion be simple, right? I mean, torsion is inevitable now, but when the torsion will be parallel, for instance. So this is another sort of simple-minded question one can ask. Now, for the issue of space form, the simplest case would be the zero curvature case, right? So, so the flat case, in other words. So, so in a joint work with Qingsheng Wang and Bo Yang, we a couple of years ago. So we gave a classification theorem for compact bismuth flat manifolds. So basically, we claim that it's just Samuelson space and their covers. I mean, under quotients. So let's recall Samuelson space. It's just a even dimensional Lie group equipped with a bi-invariant matrix. So basically, it means compact Lie group and maybe with product by vector group. So and then if it also admits a compatible left invariant complex structure, then you can make it into a complex manifold, right? So it's a classic result of Samuelson in the 1950s. So for these semi-simple compact Lie groups, and sometimes with the compensation of some vector factors, you can always equip you can always attach a complex structure on it, and then the bi-invariant matrix will be bismuth flat. So these are known long time ago. But our result basically says that they are the only such manifolds if you impose bismuth flat condition. So we first proved the compact case. Then we realized that actually by using some just purely differential geometric argument, you can actually drop the compactness. So we had another. So sort of a later proof which shows that completeness is enough. So now let me give a concrete example to show how this thing look like. So it's a compact semi-simple Lie group basically, right? So in the complex dimension 2, you only have one kind of example, namely just SU2 cross R. So that's the only group you have. And then as a compact quotient, it's a Hopf surface, right? But it's not just any Hopf surface, it's a special kind of Hopf surface where the two complex numbers A and B will have the equal module, equal norm. So we call this, we give a name, we call it isosceles Hopf surface. So A and B can be different, but their norm has to be equal. So only in that case, you have a matrix that is bi-invariant, SU2 bi-invariant. So so that's the only bismuth flat surface basically. Okay, so so now let's move on into the second part. We are interested in two types of spatial Hermitian manifolds. One is what we call BKL. Bismuth Kähler-like. The other one is bismuth torsion parallel. So bismuth torsion parallel, because these names are so long, so we use acronyms. BTP means the torsion is parallel with respect to the connection itself. Okay, so here, let me give a little remark. So in this business, it doesn't matter which torsion you use within the Gaudoshun family. The Gaudoshun connection is the line joining the Chern connection and bismuth connection, right? So in the non-Kähler case, this is a genuine line. So you get a one parameter family of connections. Now each connection has its own torsion, right? I mean, they're all related. They can all sort of be represented by one another. So it doesn't matter which T you use for the torsion part. So if one is parallel under nabla B, the others will be parallel under nabla B as well. So in a way, but on the other hand, if you replace nabla B by another Gaudoshun connection, then it's inequivalent. It's quite different actually. So so it's important to it's not important which torsion within the Gaussian family to use, but it is important the torsion is parallel with respect to which connection. So so that's why we put bismuth torsion parallel. You know, my English is not native, so we don't know how to coin the term properly, but we try to reflect this point, which I don't know if we're successful or not. I'm sure for a native speaker, you probably can come up with a better name than this. Okay, so the other. Okay, so I always find it a little awkward, and the name is not a good, not a perfect term. Okay, so the other term is BKL, so which means bismuth Kähler-like. It means that the curvature, which we denote by RB of this bismuth connection, obeys all the Kähler symmetry, you know, enjoyed by the curvature tensor of a Kähler matrix. Namely, first of all, here we're using complex coordinates. So first of all, you only have I, J bar, K, L bar components. The other components are all zero. So here I didn't mention the IJKL component because that's automatically zero because it's a Hermitian connection, right? So last two position has to be one without bar, one with bar, right? But the first two position, you know, there could be two zero components. So in general, it won't be zero. So if it is zero, and if the first and the third position can be swapped, then that's what a Kähler-like means. These are all the Kähler symmetries, right? So so if you impose the bismuth, if you impose the condition that the bismuth curvature behaves like the Kähler case, then this is a restriction, right? It doesn't imply the matrix has to be Kähler because there are non-Kähler examples, such as the half surface we saw, right? In which case the bismuth curvature is totally zero. So of course it obeys all these symmetries. So, but on the other hand, it's a non-Kähler surface, right? So the matrix can be non-Kähler, still the rather special where the bismuth curvature still enjoys a lot of symmetry. So that's the Kähler-like condition. So there were this conjecture proposed by Angela and his collaborators. So 4 people. So they basically conjecture that any compact BKL manifold must be pluriclosed. Pluriclosed is also called, I noticed that called SKT, right? In especially physics literature. So basically, but if you think about these two, so first of all, we give a remark. So under this BKL assumption, it's very easy to see that the pluriclosed condition is actually equivalent to the BTP condition. So the above conjecture can be rephrased as BKL implies BTP. So BKL is a requirement just on the curvature, right? A bismuth connection. And BTP is a condition put on the torsion of the connection. So it's the first derivative of torsion equal to zero. So again, it's a second order condition, right? But one is curvature, the other one is torsion. So we know in differential geometry, it's often a mystery between what's the relationship between curvature and torsion, right? So it's tangled up, but oftentimes it's not so clear. So this conjecture was proved by Zhao and I a few years ago. So we confirmed this conjecture. I should mention that BKL was a topic studied by quite a few people in recent years. So here we give a few examples. So the original one was this for AOUV, right, for people. They classified all the BKL threefolds amongst these three-dimensional complex neo-manifolds and a Calabi-Yau type complex soft manifolds. So they are altogether maybe 30 or so. It's fully classified, right? So they basically just check case by case. and found out all the BKL ones. And then they realized all these BKL ones happens to be pluriclosed at the same time. So they wonder if this is a phenomenon that is that will be sustained beyond these neo manifolds and soft manifolds of dimension 3. So so that's how they came up with a conjecture, I believe. So so we also sort of use their thoughts, and we just look at the simplest kind of algebraically simplest kind of manifolds we can get our hands on. So namely the neo manifolds. So we were able to classify all the BKL manifolds among actually a special type of neo manifolds. Namely, we wanted the complex structure J to be also nilpotent. So this is a sort of the most benign type of neo manifolds. So in dimension 2, the situation is rather simple. Namely, this BKL, BTP are equivalent in dimension 2. And also they're equivalent to a special kind of locally conformally caterness. It's called vestment. So vestment means locally conformally cater, but its Lie form is parallel with respect to the Levi-Civita connection. So it's a special kind of locally conformally cater. And the Belgang gave a beautiful classification theorem in 2012. So basically he classified all the compact non-cater vestment surfaces. So they're just either the Kodara dimension 1 non-cater proper elliptic surface, or Kodaira surface, which are affine quotients of the C2, or some Hopf surface, including the so-called elliptic ones and class 1. So so of course you see it's more than just the B-smooth flat ones, right? So so in a way, the BKL or BTP are fully understood in dimension 2. So if you want to study it, start with dimension 3. In dimension 3, Yao and Zhao and myself also had a classification theorem. So we basically did 3-dimensional complete ones. They turned out to be just the product of 2 Sasaki 3 manifolds with a standard product matrix. So for instance, SU2 cross SU2, right? That's the Calabi-Ekman. But not all the complex structure, just the standard one. You cannot twist it. If you twist it, then it's no longer BKL. So so BKL manifolds form a very restrictive, highly restrictive class. So in dimension 3, basically our classification theorem says that there's not much, right? So in higher dimension, if you look at the sample in neo manifolds, then they must be step 2 neo manifolds with abelian complex structure, and also fulfill. You can explicitly write down the structure equation in a simple form, a relatively simple form. But in dimension 4 and above, so dimension 3 is still rather special for this kind. But in dimension 4 and above, still we have no idea how to classify this class. So dimension 3 is still special for this type. So then for general dimensions, we in this paper of Yao and Zhao, with Yao and Zhao, we had some sort of structural results, but only kind of sporadic here and there. For instance, we showed that it doesn't admit any Hermitian symplectic matrix. Hermitian symplectic means that you can add a 2-0 form to this scalar form to make it a symplectic form. So now Hermitian symplectic is more special than pluriclosed, right? So if it's Hermitian symplectic, it is automatically pluriclosed, but not vice versa, right? So but if the manifold satisfies Didi-Bao lemma, then the converse is also true, right? Namely, pluriclosed and Hermitian symplectic are the same. So so our result shows that BKL manifold, they're pluriclosed, right? But they're not Hermitian symplectic. So in particular, they cannot be Dirichlet manifolds. And they're always Gaussian, and actually they're all always K-Gaussian in a way, but they cannot be strongly Gaussian in the sense of Popovich, which means that the Kähler form, when you take wedge power to the n-1, n is a complex dimension, then the partial of it equals to the partial bar. It's partial bar exact. So this is a condition sort of weaker than balanced, right? But it's useful in the study of spatial deformation theory. So therefore, it's invented by it's introduced by Popovich. So so what we can show is that on a compact non-Kähler SKT BKL manifold, the matrix itself is not strongly Gaussian, but you cannot admit any other strongly Gaussian matrix. In particular, there's no other balanced matrix, right? So there is this famous conjecture by Fino and Vezzoni, and maybe so in that area. So they say that compact complex manifold, you cannot simultaneously have a purely closed matrix and a balanced matrix unless the manifold is already admits a Kähler matrix. So so that conjecture is has a lot of supporting evidence now, but it's still not, it's still an open question, I think, right? The most general case. So so we in our paper we also raised a whole bunch of sort of speculations, you know. So basically we check in dimension 3, they're valid. So we wonder if it's, we believe it should be true in higher dimension. For example, for BKL manifold, even though we cannot classify it, but we look for this so-called Ricci flat case, right? So if the Ricci, we wonder if there are Ricci flat ones that are non-flat, but in dimension 3, the vanishing of the Ricci curvature forces the full curvature tensor to vanish for B-smooth connection. So so we made a conjecture. We think it's true in higher dimension as well. So it's unknown in dimension 4 and above. We also made a conjecture that in dimension 3 and up, non-Kähler BKL compact manifolds cannot admit any locally conformal Kähler matrix. So this is in contrast with dimension 2, right, where all the BKL matrices are locally conformal Kähler, right? So in dimension 3, all of a sudden you know LCK structure no longer is compatible with this type. So in dimension 3, but we cannot prove it in dimension 3 or beyond, but we can prove a weaker result, namely such manifold does not admit any other Westman matrix. So Westman is you know more special than locally conformally Kähler, right? So so our argument doesn't, I mean, need the Westman structure. So another conjecture we propose is that if for non-Kähler BKL, if you impose the if you require the canonical line bundle to be trivial, then it's basically the neo manifold case. Namely, you can namely when you allow both the matrix and the complex structure to deform, to continuously change, then you can move it into a neo manifolds. So, but all these conjectures are open in dimension 4 and above. In dimension 3, because we have a classification, so you can check, right? Okay, so now let's move on to the BTP part. So BTP is a considerably bigger set than BKL. The definition, as we mentioned before, is just torsion parallel. So by this LUV conjecture, so BKL is a subset, but it is a proper subset, right? So so the first question one like to ask is that can you characterize BTP condition just by the curvature? Because BKL is just defined by curvature, the symmetry of curvature, right? So we Zhao and I basically we try to understand our proof of the AOUV conjecture. The proof is algebraically kind of complicated. This is before Lafontaine and Stanfield proved their Gaudushun flat paper. So their computation is actually more involved and more thorough than ours. So, but when we prove this AOUV conjecture, it's, we kind of checked it's correct, but we don't quite see the geometric insight. So we try to dig it a little bit deeper, and then we found actually this BKL. So we proved the following characterization theorem for BTP manifold. So the statement is somewhat longer. So it says the following. If you have a Hermitian manifold, then it is BTP, torsion parallel, if and only if the following set of conditions are all satisfied. So the first one is the curvature doesn't have the IJKL bar component. In other words, you only have IJ bar, KL bar components. The second one is kind of like Kähler-like, but a little bit weaker. So when you interchange the first two positions with the last two positions, the curvature remains. Okay, so this is not as strong as interchanging the first and third, because if you can interchange the first and third by taking conjugation, you can also interchange the second and the fourth, right? So therefore, the first two and last two will be interchangeable, right? But here we only require you simultaneously change the first two and last two. So it's a weaker symmetry requirement. Now, the third and fourth condition impose on this Q tensor. The Q tensor is just the interchange the first and third. Okay, so so you may not be able to interchange. So it may not be symmetrical with respect to the first and the third. So in other words, Q may not be zero. But Q, even though Q may not be zero, but the Ricci of Q, this is the first Ricci, right? So you contract the last two positions to get the first Ricci. So the first Ricci of Q must be parallel. That's a two tensor, right? And also Q itself must have a kernel. The kernel is X is a direction, tangent direction, due to the so-called Gaudushun torsion one form. So in other words, when the matrix is not balanced, it may or may not be balanced, right? So if it's balanced, of course, this condition 4 is vacuum. If it's not balanced, then you have this torsion one form corresponds to a 1,0 tensor, a 1,0 tangent vector, right? So this 1,0 tangent vector must be in the kernel of this Q. Okay, so that's the condition. So you realize that this theorem implies the solution to AOUV conjecture, because BKL means condition 1 plus Q equal to 0, right? So if it's BKL, then all 4 conditions are satisfied. In which case, the theorem says that it's BTP. So BKL implies BTP, right? So one direction of theorem A guarantees AOUV conjecture. So we should also remark that BTP doesn't imply the full Q is parallel. Okay, because there are examples of BKL manifold with the curvature is not parallel. So Q, so let me give some examples of BTP manifold that are not BKL. So for instance, in the Neo manifold case, we could also mimic our characterization of BKL to characterize BTP. The characterization is actually much easier to describe. So a complex Neo manifold will be BTP if and only if you can find a unitary coframe, which we call phi. And then the first R forms are closed. The remaining forms are not close, but their differential is can be simultaneously diagonalizable, expressed only with the 1-1 part from the first R. So this is a two-step nilpotent, and the complex structure is abelian. Abelian means that there's no 2-0 components, 2-0 forms on the right-hand side, right? Only 1-1 forms. So just from the description for neo, you know that BTP is a much broader class than BKL. So to give it a specific, so let's just look at the three-dimensional case. In the three-dimensional case, let's exclude the killer one, the trivial one, the abelian one, right? So the neo manifolds, if it admits a BTP, then you will have R is necessarily 2. So the structure equation look like this. You can normalize it so that the first leading coefficient A is positive, right? So then U can be any complex number. Okay. Now BKL means U is pure imaginary. Okay, under this normalization. So of course balanced is just 1 point, right? When the sum equal to 0. So U is minus A, right? So you see that this gives us kind of a picture. BTP is a broader class, right? So in this case, it's parameterized by U, by all the complex numbers. So a line, the y-axis represents all the BKL, right? Away from this line, so you could have even balanced ones. BKL can never be balanced unless it's scalar, unless it's trivial, right? So another example are all the Westman manifolds. So it's a recent result by Andrada and Villacampa. They show that any locally conformally killer manifolds is BTP if and only if they're Westman. Okay, so this also gives a nice characterization of Westman manifolds from a different angle. So for instance, if you look at this simple standard Hopf manifolds in any dimension, they're always BTP. So we Zhao and I, we also obtained the observation, namely, even in the local case, if you have two conformal within conformal class, if you have two different matrix that are both BTP, here we have a technical requirement. We want this this conformal factor to be non-trivial, non-constant in an open dense subset. And then both matrix has to be Westman. Basically, only in the Westman case you can have non-uniqueness within conformal class. In the compact case, this is obviously true because BTP matrix are always Gaussian. So Gaussian matrix is certainly unique within a conformal class by constant multiple, right? So okay, so in the third part, we focus on threefolds. Okay. So especially we're interested in understanding the balanced ones, because non-balanced ones, remember you have this spatial direction that is in the kernel of the curvature. So in a way, the holonomy is reduced, right? So non-balanced in a way it's easier to analyze for BTP manifolds. So because it gives you sort of kind of like Westman manifold, gives you a handle, gives you S1, not quite an S1 action, but a parallel sort of a parallel vector field. So for non-balanced BTP, they resemble BKL in structure in many ways. So where you can write, you can find a special frame, a local frame, so which we call admissible frame, under which the torsion tensor behaves in a simple manner. So here, let me give a sort of a brief description. So for non-balanced BTP manifold, you always have, around any given point, you always have a special frame under which the torsion behaves simple and curvature behaves simple. So in particular, the Bismuth connection has reduced holonomy group. Okay, and there is this Lewis potential condition introduced by Belgam, which says that so this condition is given in terms of the Chern, in terms of Keter form, the differential of the Keter form. So d omega has to be decomposable in a simple way. So that's what he called Lewis potential. I think initiated by people like Ornia and Gadushun, and also studied by Belgam. So we show that for BTP manifold, non-balanced BTP manifold, this LP condition is equivalent to the degenerate torsion condition, which means the torsion has a lot of zeros. Okay, so in particular in dimension 3, non-balanced BTP, just this category just coincide with Belgam's so-called GCE manifold. He called it generalized Calabi-Ekman. Okay, so and he gave a rough classification of it. So in a way, BTP, in non-balanced BTP, but his classification is not really a classification. It basically like deforming each class. It's a description basically. So so now let's focus on the balanced ones. So BTP, unlike BKL, can be balanced, and these we found that to be rather interesting. So the neo-manifold example we saw is an example. It's balanced, and so when U equals to -A, right? So that one is balanced. So we found one neo-manifold example. But then there are other examples. For example, this complex simple Lie group, right? Complex Lie group. So this is a Chern flat. You can check it is balanced BTP. Another example is more is kind of a more subtle. So this is what we call Wallach threefold. So as a complex manifold, it's just the flat threefold, namely the hypersurface in P2 cross P2 of type 1,1, right? But the matrix is not a standard Keter-Einstein matrix. It's a standard Keter-Einstein matrix minus the square, minus minus this 1,1 form. So these are if you use Z and W to denote the standard coordinate, then this is well defined. So this is a Hermitian matrix. It's still positive definite. So omega is a Hermitian matrix. And one can check that this matrix is this non-Keter matrix is balanced and BTP. Okay, it has a nice curvature behavior. For example, its Griffiths curvature are non-negative, right? Its Riemannian curvature for the Levi-Civita connection is Einstein, and having and also having other nice curvature properties. So so here let's introduce a term we call middle type. Namely, if you look at the B tensor of a Hermitian manifold, which is formed by the curvature by the torsion, right? So you contract the lower two indices of the torsion tensor, you get a 1,1 tensor. So this is globally defined on any Hermitian manifold, right? So it's always non-negative, global 1,1 form. So that's the B tensor. If you look at the rank, namely the number of positive eigenvalues of B, then we in dimension 3 it can be either 1 or 2 or 3, right? So if it's 2, which is the middle one, so we call it a middle type. Okay. In this case, the eigenvalue actually turns out to the positive eigenvalue will have to be equal because of BTP requirement. So then we found some examples. There are 4 families of Lie groups that can have compact quotients with this BTP requirement. So one can explicitly write down their structure equations. Okay, so it depends on some parameters. Here, A, B are real numbers. The other letters are complex numbers. Rho is with norm 1, and W is not independent. W depends upon U and V in such a way. Okay, So there are 4 families, A, B, C, and D. Okay, so one can write them down explicitly. So when the parameters are 0, they all reduce to the neo manifold case. So in a way, you can think of them as the neo threefold, so deformed out, right? So these ABCDs in general are not nilpotent anymore, right? So these 4 families are all the middle types. If you require to be a Lie group to begin with, right? So basically, so we call it Lie Hermitian manifolds. So then up to scaling, these are, so this is a small classification theorem. Now, for 3-dimensional compact balanced BTP manifolds, we have a full classification theorem. So again, the statement is a bit long. So let M3 be a non-killer compact balanced BTP threefold. Then up to scaling, you're in one of these 3 cases. So depending on the rank of the B tensor, if the rank is 1, then it's just the Wallich threefold. That's a Fano manifold, right? So if the rank is 3, then you only get the semi-simple, the complex Lie group case, a compact quotient or complex Lie group. So this is a Chern flat case. And then the majority lies in the middle type. So in this case, what we can prove is the following. So there is a double cover of M. Well, this covering degree can be either 1 or 2, depending on there's this line bundle. This line bundle could have degree 2. It's a torsion class. So then once you lift to this possibly double cover, then there's another complex structure compatible with the matrix. So you have 2 basically Hermitian structures with the same matrix. So one we denote as I, the other one is our original J, right? And this I and J are I and J commute. See, there's no minus sign. So this is not like the hyperkiller case, right? So hypercomplex case. So this is just abelian case. So with one complex structure, the threefold becomes Westman. With the other complex structure, it's the BTP. So because Westman, there's a nice structure theorem by Verbitsky and Ornia. It's a nice theorem. It says that such manifolds are fiber bundle over S1, where the fiber is a Sasaki manifold. So in this case, we kind of know the topology of the manifold M hat a little better, right? So it must be a Sasaki 5 manifold fiber bundle over S1. And this Sasaki 5 manifold is also rather special. It has 2 Hermitian structures on it simultaneously, I and J, that commute, right? So we call it abelian bi-Hermitian structure. So in higher dimensions, we also have some generalizations, right? So in higher dimension, it's kind of this kind of phenomena persists. So furthermore, so on this middle type non-killer balanced BTP threefold, there's no pre-closed matrix on it. So it doesn't admit any pre-closed. So this is in sharp contrast with the BKL case, right? Where the BKL matrix are all pre-closed, right? So it doesn't admit any other pre-closed, which is not surprising because we require the original matrix itself to be balanced, right? If you have a balanced matrix, you don't expect any pre-closed matrix. So this gives another evidence. Here, let me say a few words about the first case, case 1. Case 1, the proof roughly goes like this. You have this torsion line bundle that I mentioned, which basically in this case shows the structure equation, analysis on the structure equation and curvature implies that the manifold, the threefold has to be a Fano threefold with index 2. So it's either CP3 or a Del Peso threefold. So the Del Peso threefold is fully classified by Fujita. So there are 7 types, right? So but most of them you can rule out just by considering their Euler number, because these are I mean, these Fano threefolds are fully classified. These numbers are well, not Euler, by their second Betti number. So it can be ruled out, except the CP3 case and the flag threefold case. So the CP3 case can be ruled out by explicit computation, and the flag threefold case leads actually to example. So it's an interesting phenomenon. For example, if you look at all the Kähler C space, some qualify, some does not. CP3 doesn't qualify, but flag threefold does. So we still don't quite understand, just for Kähler C space, what's the deal here? So that's in higher dimension. That's an interesting question to explore. This is the second result that I like to report. So here I didn't say anything about the proof, but here I give a little bit of an argument for the first case. For the second and the third case, it's kind of similar. You basically start from the structure equation and analyze how the curvature, I mean, this curvature represents some topology, right? Like Chern class and so on. And just by some analysis, you can lead to these conclusions. Okay, so I'll stop here, and I thank you very much for your time. Yeah, thanks.
Thanks. Yeah, let's thank the speaker. Are there any questions? I was curious about this, like somewhere in the middle, you mentioned these like Lie form with potential structures or something like that.
Yeah. So that's that is condition introduced. I think it was introduced by maybe Ornia, Gadushun, or Verbitsky. I forgot exactly whom, but it originated in their study of I think locally conformally Kähler manifolds. But then I think where I learned it is from Belgaum's paper. He studied this condition, and basically it's a condition imposed on the differential of the Kähler form. So when you d omega, right? So in general, the full torsion will appear, right?
Mm-hmm.
But if you require it equals to just some one form, like the torsion one form wedge omega, plus some other terms in terms of the differential of this one form, right? Like if you call this one form eta, it's like eta wedge d eta or something.
I see. Okay.
So basically, you require the torsion of this Hermitian matrix to be somehow degenerate, in a way, right? So that's a condition they use, and then that's how Belgaum come up with his term of generalized Galabi-Ekman. So he called it GCE. So basically, he wants the Bismuth connection to have parallel torsion plus this LP condition. So that's what his GCE means.
Okay.
Yeah.
Okay.
But in this definition, you want this torsion one form to be non-trivial. In other words, you want the manifold to be non-balanced. If it's balanced, then you don't have this LP business.
Right. Okay.
So yeah.
Okay. Yeah, thanks.
Yeah, I should say that this parallel torsion thing wasn't started by us. I mean, in the literature here and there, they call it a canonical connection, right? I mean, you're the one of the pioneers to study Bismuth connection in math literature, right? So we actually read your paper, and got interested in this connection.
Oh, okay.
Because
Okay.
early on, people don't, math people don't use this connection for a lot, right? Except
Sure,
maybe
yeah.
maybe
Not
people
so-
at the Italian school, the people
Right.
like Fino, Vezzoni, right? I mean, they're pretty involved with this this non-killer. I mean, I'm kind of new to the to the non-killer business myself,
Sure, yeah.
but
It's quite a
this is
jungle. Yeah.
yeah, this is quite an interesting connection, quite
So,
fascinating to me.
yeah, for sure.
Yeah, what we did is basically a first order study. So it's not kind of superficial in a way. We haven't got into the second derivative a whole lot, namely the Buckner, Weizenbach type thing. It's
Right.
still a little, so it's still at a preliminary stage. So when you study flows like this, I mean, you get into all the orders already, right? So in a way, it's more thorough, but we're still paying attention to this tanglement between torsion and curvature, which are algebraically quite interesting, but quite complicated to us. So we want to figure out what the implications are. And then the logic next step would be move on to study deeper stuff like the Weizenbach formula and so on, right?
Yeah, sure.
But we're not quite there yet.
Sure.
Yeah.
Well, okay. Are there more questions? If not, let's thank Feng Yang again. Thank you for the nice talk.
Thank you all for your time. Thanks, Jeff, for the kind invitation. Yeah.